When I was in high school, I guess I didn't say that in the podcast, but I also watched a lot of Numberphile. And so the fact that you're saying this is like this is a Numberphile style interview is kind of bringing back some memories.
Great.
But what I'm going to say is not as prepared as Numberphile, so I hope you'll forgive me for this.
Of course.
Yeah, so I want to talk a bit about, I guess, algebraic K-theory, which is the main thing I do. Even though it's in the field called algebraic topology, it's actually more focused on algebra these days. So the basic principle of algebra is that we study equations. And for just 1 second, I'll stick to polynomial equations. And these are equations of the form maybe axy plus bx squared equals 0, where x and y are variables and a and b are fixed parameters. They're fixed on you, and you have to find x and y satisfying this equation. And one of the first things you learn last things you learn maybe in high school is that whether or not there are solutions to this equation really depends on what you mean by solution. For example, let's look at this equation. Oops. I went one step too far. If you're like an ancient Greek and you only allow rational numbers, then there are no solutions to this equation. But if you accept the real numbers, then there's two solutions to this equation, which is square root of 2 and minus square root of 2. And so this tells you already that there's a big difference between where you want to solve an equation, whether you want to solve it maybe over the rational numbers or over the real numbers. And if you know a bit more about math, you know that there's also the complex numbers where you can solve equations like these, x squared plus 1 equals 0, which has solutions plus and minus I, as opposed to the real numbers where there are no solutions. And I want to view these as not just different places where you can solve equations, but different places where you can do algebra. So there's an algebra of Q, there's an algebra of R, and an algebra of C. And maybe one way to organize this is to think about the category of Q vector spaces. So this is a mathematical object that's a bit more complicated than each of these because this is just a set of numbers, but this is instead the collection of all vector spaces over Q organized as this one single object. And in this context, a priori you can only study sort of linear equations that are much simpler. That looks maybe like this. And there it may seem like there's not really a difference between these two places because in the equation of this form, if a and b are rational, it has a solution here if and only if it has one here and here. But this category, this object has more structure, and in fact, if you take into account this more structure, you can end up talking about these other kinds of equations. And so this context is sort of one context where you can talk about algebraic equations and then having different solutions here and here. And once you see this, you see also that you can, there's actually more examples of structures like this than the ones given by the similar symbols like vect R and vect C. There's actually a lot of other contexts where you can talk about these kinds of equations. And I guess the most general kind of place where you can do algebra, in my mind, is something called the stable infinity category.
Okay, now this is a big jump.
This is a very big term. And the ones that I wrote here aren't literally examples of this, but they're sort of, even though they're not examples of that, they're sort of subsumed by this concept. And you can even add some more adjectives to make this even more complicated. You can add like the word that allows you to talk maybe about polynomial things that aren't quite linear, which would be something like symmetric monoidal. So it's a lot of symbols and a lot of words. But basically what this means is like some kind of collection of objects, where one can do linear algebra. And to give sort of a flavor, like an example of a flavor of the kind of thing you can do, let me point out that, for example, there's an extra thing that isn't quite one of those, but closely related is the quaternion numbers, which is also some kind of number system, but unlike these three ones, it doesn't satisfy one of the fundamental equations of math, which is AB equals BA. So it's not a commutative thing. And you can also take vector spaces over H, but you can do some much more complicated things. For example, you can consider the stable infinity category of sort of matrices, which is like the objects, instead of being just vector spaces over Q, are going to be vector spaces over Q equipped with a linear operator.
And as you learn in linear algebra, a linear operator is nothing else than a matrix.
Exactly. So yeah. So this V here, let's say it's finite dimensional, is isomorphic to maybe, let's say we're over Q, is isomorphic to Qn for some fixed n, and this F is then entirely prescribed by a certain matrix of n by n matrix, and the properties of this matrix are reflected in properties of this object, or certain properties of this matrix are reflected in properties of this object in this context of linear algebra. And you can see this is not quite the same as vector spaces over some number system. But you can still study this within this context of stable infinity categories. And one thing that I really like is, instead of fixing one stable category, instead of studying that one specific one, is observing how they relate to one another. So if you think about here, for example, between, I should maybe get more room. If you think about R vector spaces and complex vector spaces, these are not just two abstract collections of things, they're actually related. They're related by things that are called functors, which is another complicated word. But for example, the simpler one, maybe it goes in this way. It says that any complex vector space, well, you can multiply by complex scalars, but among complex scalars you have real scalars, and so you can also multiply just by real scalars. And so this tells you that any complex vector space is also a real vector space.
Okay.
And it turns out there's also something going the other way, which is called complexification. It's a bit of a more complicated operation. But from the perspective of dimensions and matrices, it's sending a vector space to a vector space of the same dimension, but now over the complex numbers. And if you have a matrix consisting of real numbers, I don't know, then you can see them also as complex numbers, and so they also give you a matrix here. And you can see studying the interaction between these two things along either of these sort of operations helps you relate how you can solve equations here or there.
Okay.
And so this interaction between these various things is maybe the study of these stable infinity categories. And I don't know how much, but
you can keep going.
There's many ways of studying those, and there's one particular invariant of stable infinity categories, which is called algebraic K-theory. And that's maybe my favorite invariant. So that's sort of the main object that I study these days, at least. And one remarkable thing about this is that it's a super abstract thing that has to do with these sort of super abstract stable infinity categories, which are all very complicated words. But this has connections to a lot of various fields of mathematics. In particular, it has really surprising connections to a field called geometric topology, which is one of the reasons, but not the only reason why this field of research was, for a very long time, associated with algebraic topology. And in particular, for every sort of shape, for every space, like a donut, the favorite drawing of topologists, maybe let me do a two-hole donut. For every such shape, there's one or even maybe several different contexts of linear algebra, so stable infinity categories, you can associate to it. Let's call this X, and maybe there's a bunch of different ways of associating to it a CX. And it turns out that properties of the CX, or properties of its algebraic K-theory, have some deep relation to the properties of this space. And that's one of the motivations to study this gadget, which is a very, very interesting gadget. And what is this algebraic K-theory? So it's again a very complicated gadget itself, but it has a very simple shadow, which is something called K0. And maybe I'll conclude with the definition of K0, which is that if you plug in one of these stable infinity categories, K0 of C is going to be sort of the best possible place where you have a notion of dimension. So best recipient of a notion of dimension. What does this mean? Well, vector spaces, as I said, they have this dimension. And in fact, they're completely classified by this dimension. This is a very simple thing. If you want to tell me what the vector space is, you can just tell me a number. But if we look here at vector spaces with an endomorphism, so matrices, it's much more complicated to classify them. And if you think about Jordan normal forms and so on, you'll find that you can actually classify them, but it's much more complicated.
Okay.
And so they have a dimension, which instead of being just a number, is a bunch of numbers plus some data.
So it should completely classify the thing, or what is a dimension in this general
Right.
thing?
That's an excellent question. You can try to think of it as classifying the thing, but it doesn't necessarily actually end up classifying the thing.
Okay.
It's so a dimension is some kind of function. Maybe let's call it chi. By analogy with topology, it's some kind of function that you can assign to each object. And it's supposed to satisfy a bunch of axioms. So the simplest of the axioms is that if you take something called a direct sum, you're going to end up getting a sum of the dimensions. But there's a more complicated axiom involving something called cofiber sequences, which, among other things, forces you to lose some information. So this loses some information, but it's if you want something that's subject to these relations, and the one that I haven't written, it's the best one that you can get.
Okay.
And so if this one loses some information, it means that any notion of dimension you could have come up with would have lost information as well. And this is why this is an interesting object to study, is because maybe you want to classify the objects, and you want to see how far you can get with just functions that satisfy these properties.
So does it now help me also to classify my shapes?
It can actually help you classify your shapes, yes. There are some very famous conjectures that are proved in certain cases and open in some other cases, which say, oh, if the algebraic K-theory has such and such property, then all shapes of a certain kind are classified. The historical origins of algebraic K-theory also have something to do with classifying shapes and the various notions of finiteness of shapes. You can imagine that this is something that's kind of finite because you can think of it as really being in a closed enclosure. But if you're given an abstract shape and you don't know where it comes from, it can be difficult to decide whether or not it's finite. And in what different senses it can be finite. And one of the original applications of algebraic K-theory was coming up with a criterion for this.
Very nice. Thank you very much for this nice introduction.
Yeah, thanks.